Hi, this is the second video for Chapter 2 highlights. This covers the topics of histograms and some other statistical graphs. First of all, a histogram is just a bar graph where the horizontal scale represents the classes of data values and the vertical scale represents the frequencies. So in other words, a histogram is just a frequency distribution put into a graph form. Notice between this frequency distribution on the left side and the histogram on the right side, we have the classes becoming what's on the horizontal axis for the histogram, and the frequencies become the vertical axis for the histogram. We can also do a relative frequency histogram or a percent frequency histogram just by using a relative or percent frequency distribution and graphing that. So again, on the horizontal axis for our histogram we have the different classes, the different data values in other words, and this time on the vertical axis we have either relative or percent frequencies. And one of the most important things that you need to learn in this class is to be able to interpret different statistics and graphs that you're presented with. So in this case we've got a histogram and we want to look at some different characteristics that we can see from the graph. So some different things that we're concerned with this histogram are what's the class width, what's the highest frequency bar, what's the lowest frequency bar, what kind of shape does the distribution show, and so on. So if we are trying to figure out our class width in this case, notice that we don't have specific markers that divide up our bars specifically. So we're going to have to do a little bit of figuring out to know what our class width is. So two of them that we can actually see, if you notice where this bar starts, we have a 60, and at the end of this bar we have a 70. So between 60 and 70 we've actually covered 5 classes or 5 bars. And that tells us that the class width would have to be 2. So this bar is going from 60 to 62, 62 to 64, to 66 to 68, and to 70. Okay, so our class width is 2. Then if we want to know if this is all we have to tell us about the data, one of the things that we'd like to know sometimes is what's the minimum possible data value and the maximum possible data value for this set. So to look for the minimum data value, we've got the 60 marked right here. We know if we go down to this class that would be 58, and that means this first class starts at 56. So our minimum possible data value is 56. And we can do the same thing on the right end of the graph. We've got a 70 marked here. The end of this class then would be a 72. So the maximum possible data value is 72. And last of all, we'd like to know what's our highest frequency class. Well, it's the one with the highest bar, this one that has a frequency of 324. And that, again, we'd have to figure out where this is. This would start at 62, and the next class starts at 64. So the class with the highest frequency in this case is the class that goes from 62 to an upper class limit of 63. Okay, the next type of graph that you're going to be looking at in this chapter is a stem plot, or a stem and leaf plot. And all we're doing with these is taking the original data that we have and separating it into stems and leaves. So for example, if we had a data value of 50, if our stem is the tens place, then the 5 out of the 50 would go in the stem, and the 0 would go over here as a leaf. If we had another data value of 54, then the 4 would go over here as a leaf. This is actually a nice way of getting a frequency distribution because you automatically know now how many values are in each class. This class would represent values from 20 up to 29. The next one would go from 30 to 39, and so on. And some statistical software, if you ask it to do a stem and leaf plot, it will actually give you the count for how many values are in each stem. That's a great, easy way to get a frequency distribution. Okay, then we have bar graphs, and these are pretty much the same as histograms, except that they can be used for qualitative data, not just quantitative data. So this is basically a frequency distribution for qualitative data that's put into a graph form. And in this case we had something to do with telephone services, and notice that we've got these different categorical values down here, and then we have frequencies for each one. And a little offshoot of this is if you want to do a Pareto chart, that's just a bar graph where you arrange the bars according to their frequencies, with the highest one being on the leftmost side. Okay, then we have a pie chart or a pie graph, and this is especially helpful if you have a relative frequency distribution. You can easily convert that into a pie graph. In this case, notice that the values are frequencies. You can also do a pie graph with the values being percentages. And we also have scatter plots. Use a scatter plot when you have two different variables. So we have one variable on the horizontal axis, another variable on the vertical axis, and we're basically just plotting points. So for example, a point down here might represent having 880 chirps per minute and the temperature being 69 degrees. We use these to look at whether there might be a relationship between the two variables. In this case, it looks like as the chirps per minute increases, the temperature always increases and also increases, and vice versa. So there might be a linear relationship between those two. Finally, we have cross tabulations, or we usually just call them crosstabs. We'll look at these later, and they will also be called contingency tables. All this does is it's a table that summarizes data for two variables, and we might take this out of sort of unsummarized data, and then we put it in a nice table like this to get a summary. So this would be a crosstab of some different causes of death and related to whether the person was a smoker or a non-smoker, and then what their cause of death was. Okay, now another thing we really want to look at here is graphs and different displays that can be misleading. It's very easy to use statistics to mislead people, and it's up to you to be an informed consumer or look at these graphs and be able to pick out whether they're misleading or not. Okay, here's an example of a type of graph that can be misleading. Notice here at the bottom of this graph, the values actually start at 53 instead of starting at 0. It's a little hard to tell how much difference that makes, but if you look at just your first impression of this graph, it looks like the Democrats have a much higher rate of those who agree than the Republicans or the Independents, if you don't actually look at the numbers. But if you just get the first impression of this graph, it looks like the Democrats are way ahead of the other two parties. If we fix this so that the vertical scale starts at 0, it makes a big difference. Look how much different this graph looks than the original one. Now we can see that the differences between the three are really not very much. between 62% and 54%. So this original graph was very, very misleading. Another thing that can be misleading if you're comparing two graphs is if you have different scales. In this case, notice that our horizontal scales are the same, although the motorcycle crashes one doesn't go out as far, but the vertical scales are quite different. For the drivers killed in car crashes, this scale goes up by 5 and it goes up to 35. And for the motorcycle crashes, it only goes by 2 and it goes up to 12. So if you're just comparing these two without noticing that fact, it looks like there were actually more drivers killed in motorcycle crashes that were in this second class than there were in any of the classes for the car drivers. But that's not actually the case. Okay, another thing that you're shown very often in the media is pictographs. And these are kind of graphs with little gimmicks. They have different pictures that are supposed to represent things. And depending on the way they're drawn, they can create a lot of false impressions. They can really distort the picture. For one thing, if you double the side of a square, the area doesn't double, it increases by a factor of 4. So if you're using pictures that are two-dimensional instead of one-dimensional values, the impression you get is that there's a much larger difference between two things. And also if you use volumes, pictures that imply a volume doesn't increase by 4 if you double each side of a cube. It increases by a factor of 8. So there's even more difference there. So here's an example of something that was using volumes. Notice that in this case the upper edge of this cube might be the 18,734, and the upper edge of this would be the 74,602. But the difference between these, the smallest and the largest, looks much bigger because of the fact that a cube was used. So the volume of this cube is much bigger than the volume of this cube, and it exaggerates the difference between the two. A better way to represent this data would be just with a regular bar graph. In this case, we can see more accurately the difference between the income for no high school diploma and the income for an advanced degree. So this graph we'd consider pretty fair and objective.